So we're going to keep going with integration by parts. We've done integration by parts before, so the first part will be fairly fast, but I do have a shortcut, so I'll slow down for the shortcut. So objective is to integrate by parts using both the old formula method and a new tabular method. So just to review first, we get integration by parts from our formula for product rule. So this is if I derive two functions that I'm multiplying together, then with product rule, if I derive uv, I would get u prime v plus uv prime. So this is just product rule, but with two functions, uv. So I could say if I integrated both sides of this final answer, so my derivative of uv is u prime v plus uv prime, then I should be able to get back to the same result. As long as I do the same thing to one side of the equation as I do the other, it should be okay. So if I integrate both sides, it should be okay. If I integrate the derivative, I'm integrating the derivative, so this should cancel. So that's both the function and its opposite. On the other side, if I'm integrating u prime v plus uv prime, because integration is just addition, I should be able to break this apart into two separate integrals with the same bounds. Okay, if that's true, then I should be able to move either of these to the other side and get an equation. So I'm going to move this one by subtracting that integral from both sides. So minus integral u prime v minus integral u prime v. Okay, this one will cancel, and I'm left with the integral of uv prime is equal to uv minus the integral of u prime v, or integration by parts. Any questions on how we got here?
No.
Okay. So you guys are familiar with this and you've used it before. Where this gets a little bit tricky is when we're picking out which part of our function that we need to derive and which part of our function we need to integrate. The beauty of this formula is that we never have to integrate our u, which means sometimes when we've got functions that we cannot integrate otherwise, we can use this formula to integrate it, like logarithms. We did not have a formula to integrate a logarithm directly until we hit integration by parts, because if we set that u of x equal to our logarithm, we'll never have to integrate it directly in order to get a formula for the integral. Okay, so I've got a priority list here, which just means this is going from top priority to bottom or lower priority. So if you see an inverse trig function, that should be your top priority for u. Okay, then logarithms, then polynomials, then trig functions, then exponential functions. So if you want an acronym, we can use ILATE, which is just a priority system for deciding which one should be the function that we derive. Okay, so for our sample, I've got the natural log of x dx. Okay, on my priority list, I don't have any inverse trig functions, but I do have a logarithm. So that's my priority for u. So if I set u equal to ln x, that means u prime is 1 over x. My original function needs to be the integral of uv prime. So my v prime then has to be dx, and if I integrate that, I'll get x. Okay, so that gives me everything I need in order to plug into my integration by parts formula here. So anytime I see a u, I'm going to replace it with ln x. Anytime I see a v prime, I'll replace it with dx. Okay, so the integral of ln x dx would be ln x times x minus the integral of 1 over x times x. Okay, so when we substitute, I get this. One over x times x is 1. When I integrate 1, I get x. So I get x ln x minus x plus c. Now all of these integrals, even if you had to integrate by parts more than once in order to get your final answer, are still going to have a plus c. So you can just save your plus c all the way to the end of the problem and write it there.
Okay.
Any questions on how to use the formula?
Yeah.
Okay. So then for our shortcut, I'm going to introduce some new notation really quick. So this is differ integral notation, which is a way of writing a derivative or an integral of a function. So the notation is sort of this double D QF. If Q is positive, then we'll derive our function that many times. If Q is negative, then we'll integrate our function that many times. So if I told you d4f, that would mean the fourth derivative of f. But if I told you d negative 2f, that would mean the second integral of f. So we'd integrate twice. Okay, so here's a couple examples. d3f is the third derivative of f. So if this is a function of x and I'm deriving in terms of x, this would be the third derivative of y in terms of x, or the third derivative of your function of x in terms of x. Similarly, if I was going to take the second integral of f in terms of x, I would integrate f of x first, and I would take my answer and integrate that again in terms of x. Any questions on the notation?
Nope.
Okay. So what I'm going to do is I'm going to take our integration by parts formula, and I'm going to rewrite it with our different integral notation, so you can see what happens if I keep expanding this. Okay, so my first part, my answer would be u times the integral of v prime minus the integral of u times the integral of v prime. So that's uv, v is the first integral of v prime, minus the first derivative of u times v, which is, again, the first integral of v prime. Okay, so I'm going to leave all my derivatives just as primes, because we're more used to that, but I'm going to use different integral notation for all of these integrals of v prime. So my first part would look like this. Okay, if I expanded this one and did integration by parts again, my integration by parts formula where my new u is u prime, and my new v prime is d negative 1 v prime, would end up looking like this. U, v, so that would be u prime times the second integral of our original v prime, minus the integral of our second derivative of u, that's u prime, so the derivative of our new u, times again our second integral of v prime. Okay, so if I expand this, then this term here that we had for our first integration by parts, if I did integration by parts again, would become this. Okay, now I've still got an integral here, so if I did integration by parts again with this blue one, so then I could expand that again. I'm going to simplify really quick, so I'm going to subtract this first term. If I'm subtracting a negative, that will become a positive, so I'm left with this blue integral. If I wanted to integrate by parts again, I would end up with the u prime prime, the next integral of v prime, minus the integral of u prime prime prime, so that's my next derivative of u, times my next integral of v prime. You can kind of see the pattern, right? Every time I'm integrating by parts, I'm going to end up with another term, which is my next derivative of u, times the next integral of v prime. Okay, so if I keep expanding this forever, I'm going to end up with this pattern, where the integral of uv prime is equal to u times the integral of v prime minus u prime times the second integral of v prime plus the second derivative of u plus the third, or times the third integral of v prime minus the third derivative of u times the fourth integral of v prime plus the fourth.
Why do we subtract and then add?
Because every time with your integration by parts formula, you end up subtracting that integral, which means after we break apart this integration by parts, I'll need to distribute that negative sign. So for this first one, I would be subtracting my integral, which is here, which we then expanded to u prime d2 v prime minus the integral of u prime prime d negative 2 v prime. So if I'm subtracting all of this, then I'll distribute that negative sign, and that will change my sign for my integral, right?
Yes.
So that ends up causing us to alternate signs with every term. So you start positive, and then negative, then positive, then negative, positive, then negative. So u integral v prime minus u prime second integral v prime plus u prime prime third integral v prime minus third derivative u times fourth integral v prime plus fourth derivative u times fifth integral v prime. And it's just going to keep doing that pattern. Okay, any questions how we got to the pattern?
Yeah. I know.
Okay. So that's the pattern. In order to make it easier, I'm going to introduce what's called tabular integration, which is a shortcut, where we're basically going to create a table of integrals and derivatives. So this is u, and this is v prime. So I'm going to derive our u's, and I'm going to integrate our v primes. Okay, so if I derive x squared, I get 2x. If I derive 2x, I get 2dx. If I derive 2dx, I get 0. If I integrate sine, I get negative cosine. If I integrate negative cosine, I get negative sine. If I integrate negative sine, I get cosine. If I integrate cosine, I get sine. So I've created a table where I am deriving my part that I want to derive, u. Derive. And then I want to integrate everything else. So deriving this part, integrating this part. Any questions on what I did to create the table?
No.
No.
Okay. And then I want to multiply diagonally. So that's u times my first integral of v prime for my first term. And that first term is always positive. Okay, then I want to alternate signs. So my next term would be my next derivative, u prime, times my next integral. So that's 2x times negative sine x times negative 1 because my sign is negative. Plus my next one, u prime prime, is my next one down. And the next diagonal would be my next integral of v prime. So that's the second integral of v prime, which would be 1, 2 is cosine. So this is, oops, I don't have my numbers right, do I? 1, 2, 3, there we go. Okay, so here's what it would look like. Again, that's u first integral of v prime minus u prime second integral of v prime plus u prime prime third integral v prime. It's going to keep going from there. Okay, so we always start positive, so if we just create our table where I've got my u and v prime, and then you work down, so derive down for u and integrate down for v prime. Then you can connect your diagonals and alternate your signs from positive to negative. Okay, so my final answer will be x squared times negative cosine x minus 2x times negative sine x, so that's plus 2x sine x, plus 2 cosine x, minus 0 plus 0 minus 0 plus 0. So every other term is going to be 0, so this is where I can stop. And then at the very end, we always need a plus c. Okay, so if I wanted to integrate x squared sine x dx by parts, my final answer would end up being this. Okay, any questions on tabular integration?
Yeah,
No.
why is not sine x before minus x squared cosine x?
Because in our integration by parts formula, when we integrate uv prime, our first term is uv, so there's never a v prime.
Oh, okay.
So we actually don't need the sine x if I'm going to create my table. Okay, good question. Anything else? Okay, so all this is a shortcut for what you guys can already do. So here's our example one more time, all worked out. If I wanted to integrate x squared sine x, I would create a table of our u and v prime, and then connect your diagonals and alternate sign. Okay, so x squared times the negative cosine x, 2x times the negative sine x, and 2 times the cosine x gives us what we want. Okay. Now, integration by parts is relatively new to Calculus AB. It just came in either last year or the year before. So I am pulling from Calculus BC, but everything on this question would be fair game for your year's AB test. So we're told that the derivative of a function is f prime equals x minus 3 e to the x minus 3 all times e to the x, for x is greater than 0 and f of 1 is 7. Okay, first thing I want to do, I'm told that the function has a critical point at x equals 3. At this point, I want to know, is it a relative minimum, maximum, or neither? Oops. Oliver, what would you do?
Set the function equal to 0.
Okay, I'm going to set this derivative of the function equal to 0, because that's when we can tell if I've got a critical point. So if f prime x equals 0, then we have a critical point. So we're already given that. I've got my critical point at x equals 3. How can I check to see whether this point is a relative minimum, maximum, or neither?
Plug in like 0 and bigger than 3.
Okay, so we could do a first derivative test, which is plugging numbers into f prime x that are around our critical point. Okay, since this is the only critical point, you can plug in any number that is less than 3, and we should get our answer for this entire interval, and any number greater than 3, and we'll get this answer for the entire interval. So if I plug in 0 right now, what happens?
-3.
-3? Okay, so that's a negative number. And if I plug in 4, what happens?
Positive.
Okay, I would get a positive
Oh,
answer, e to the 4th. Okay. So if my slope is changing from negative to positive, then Oliver, is this a relative minimum, maximum, or neither?
Relative maximum.
To maximum. So this is saying my slope is changing.
Minimum.
Minimum, okay. I think it's just a vocab thing, but my slope changed from decreasing to increasing, so
Yeah.
this point should be a minimum. Okay, so now I just need to write out a proof for it. I could say x equals 3 is a relative minimum because um, f prime of x changes from negative to positive at the critical point x equals 3. Okay, and that should give us full credit. We did a first derivative test for this, which is fine. But is there any other way we could have done this?
the second drive.
Okay, we could have done a second derivative test. So I'm going to write that somewhere up here, maybe. So this is alternatively. I guess over here. Alternatively, second derivative test. Would have been if I derive this again. So if I derive this with product rule, then f prime prime would be equal to e to the x. So if I derive x minus 3 e to the x, with product rule, this would be f prime is 1 e to the x plus x minus 3 e to the x. If I have a point where our slope is 0 and my concavity is positive, then I should have a relative minimum at that point. Now, for this problem, I definitely would have used the first derivative test. It's way easier. I have a hard time guessing what e cubed is going to be without a calculator. But I do want you guys to be able to do the second derivative test because it is possible for College Board to give you a question where this second derivative test is going to be faster, or to ask you in the multiple choice about the second derivative test. So they'll give you information about the concavity, and they'll tell you that the slope is 0, and then ask you, is this a relative minimum, maximum, or neither? So if I am concave up with a slope of 0, we would have a relative minimum. If I'm concave down with a slope of 0, we would have a relative maximum. And then I would be neither if both of these are 0. Or if the slope is not 0. Okay, any questions on part A?
No.
Okay. For part B, I want to know what intervals is the graph both decreasing and concave up. Okay, so I'm going to copy my first derivative tests really quick since we had that in part A already. we said around 3 we were changing from negative to positive for f prime. We also started the second derivative test on the left side, so we said f prime prime is equal to e to the x plus x minus 3 e to the x. Or if we simplify, that's x minus 2 e to the x. So if I set that equal to 0 and solve for x, this is going to be 0 whenever x is equal to 2. So my concavity changes at 2. I'm going to leave a little bit more space. Got to adjust my answer after this. This is our second derivative test, about 2. I am concave up after 2 and concave down before 2. If I plug in 0, I'll be negative. If I raise e to a negative number, then it'll just be 1 over something, and it'll still be positive. So no matter what you plug in for x, this part is positive. So the only thing changing the sign is this x minus 2. Okay, any questions how I got my intervals?
No.
Okay, so I'm looking for what intervals is f both decreasing and concave up. Well, I'm decreasing when I'm less than 3. So my number line, here's 3. I am decreasing when I am less than 3.
Concave up when you're more than 2.
Concave up when I am greater than 2. So here's concave up when I am greater than 2. So my overlap here is what we're looking for. So I am decreasing and concave up when I am between 2 and 3. Okay, so I could say something like this. F of x is decreasing and concave up on the interval 2, 3. As f prime x is less than 0, so that means the slope is negative, and f prime prime x is greater than 0, and the concavity is positive. Okay, any questions on what we did?
No.
All right. And the last one, what we're really here for, I want to find f of 3. I was given the derivative, so that means I need to integrate. I was also given an initial condition. When x is 1, y is 3. And y is 7, sorry. Okay. So if I want to integrate this, I do have 2 parts to this function. Which part do you think I would need to derive? And which part do you think I would need to integrate?
The f prime integrate.
I want to integrate f prime, you're right. I want to integrate f prime x, which is the same thing as the integral of x minus 3 times e to the x dx, which is 2 different parts. Okay, which of these parts should be u, and which of these parts should be v prime? Junho, what do you think?
e to the x is u.
Okay, if I make e to the x u, then v prime would be x minus 3, and my integral would give me x squared over 2 minus 3x, which means it's getting more and more complicated. And u prime would still be e to the x dx, right? So I would actually be stuck in
Yeah.
an infinite loop. Okay.
Oh,
Again, if you're not sure, we can use our acronym, ILATE, for our priority. This is inverse trig, logarithms, algebraic functions, so that's like polynomials, trig functions, then exponentials. So exponentials is the very last thing you want to make u. Okay, so u is x minus 3 then, and v prime is e to the x. So I'm going to create a table where u is x minus 3 and v prime is e to the x. Okay, I'm going to derive u and integrate v prime. Okay, so if I integrate e to the x, what do I get?
e to the x.
E to the x. Okay, if I integrate e to the x, I get e to the x. I'm going to write on this side maybe. Wait. If I derive x minus 3, what do I get?
No, 1.
1. Okay, if I derive 1, what do I get?
0.
0. And if I integrate e to the x again?
e to the x.
E to the x. Okay, and I can do one more. If I derive 0, what do I get?
0.
0. If I integrate e to the x, I get e to the x. Okay, so now I'm going to go through and match these. So I'm going to match these diagonally for each of my terms. And I'm going to alternate the sign. Positive, negative, positive, negative. Okay, so my answer for this integral is equal to e to the x times x minus 3, which is positive. Okay, minus 1 times e to the x, plus 0, plus c. Okay, then I can simplify. So if I multiply this out, this will be x e to the x minus 3 e to the x minus e to the x is minus 4 e to the x plus c. Okay, I'm not quite done because I was given an initial condition, so I can solve for my plus c. X is 1 when y is 7. So if this is f of x, then f of 1 should be 7. And f of 1 would give me 1 e to the first power minus 4 e to the first power plus c. So we can solve for c. So that's e minus 4e is negative 3e. Negative 3e plus c equals 7. I'm going to add this to the other side, or 7 plus 3e equals c. So our final answer for f of x, ooh, that's kind of hard to see.
Where do we get the xe over x, or the -4?
X e to the x minus 4 e to the x. I distributed. So if I distribute, this will be e to the x times x is x e to the x. E to the x times -3 is -3 e to the x. Minus e to the x is -4 e to the x.
Okay.
Okay. So I've got our plus c, so I'm just going to substitute for plus c here, and then we're done. So this is f of x is equal to x e to the x minus 4 e to the x plus 7 plus 3. Okay, and then we're supposed to find the value of f of 3. So I guess I do need one more line, but if I wanted to find f of 3, I can plug in 3. So this would be 3e cubed minus 4e cubed is negative 1e cubed plus 7 plus 3e. Any questions on what we did?
No.
All right.
But I have a question.
Go for it.
Oh no, it's fine. No, I got.
Okay, you sure?
Yes.
What was your question, just in case?
It was just like why we added 7 plus 3e, but it's c, so it's fine.
Okay, cool. So for the homework, I've got a file listed as integration test. I want you to complete just the multiple choice in the first free response today. And then we're going to finish up the other 2 free response questions for homework next class. On Thursday, on Friday rather, I'm going to give you guys a take-home test. It will count as an actual test grade. It is a full-length practice test, but because I can't release any of the practice tests and we're stuck doing all this online, I've rewritten my own version of the AP test. And you guys will take that.
Okay.
Okay.
Okay, so one more time, homework integration test file. Just do multiple choice and first free response. And then on Wednesday, you'll do the other 2 free response questions, so you'll finish all 3 eventually. On Friday, your homework will be the test, and that will be due Tuesday at midnight. Okay, thank you guys so much for coming.
Okay.
Thank you.
Yeah.
Bye.
Bye.